So in this video, I am going to explain about concept session, that is synopsis of stoichiometry. We will discuss important points one by one. So in stoichiometry, we will be having these subtopics: significant figures, rounding of the numbers, mole concepts, concentration terms, oxidation numbers, types of redox reactions, and last titrations. So these are important topics of stoichiometry. So first subtopic is significant figures. So simply denoted with SF. Significant figures. So here main points are all non-zero digits are significant. That means we can count all non-zero digits. Next, zeros before first non-zero digit are not significant or never significant. We should not count the zeros to the left of first non-zero digit. Next, zeros between two non-zero digits are significant. So between two non-zero digits we can count. Next, zeros at the right to the number after decimal point are significant. We can count the zeros after decimal point. Next, counting of numbers of object have infinite number of significant figures. That means simply exact numbers. Exact numbers will have infinite number of significant figures. That means 2 eggs, 10 books, like that. That means we can place any number of zeros after decimal point. Therefore, exact numbers will have infinite number of significant figures. Next, in multiplication or division, the result should be have the same number of significant figures as the component with the least number of significant figures. This is very, very important during multiplication and division. We have to follow this rule. So answer must be reported to least number of significant figures. Next, during addition or subtraction, the result should have the same number of digits to the right of the decimal point as the number with least digits to the right of decimal point. That means in case of addition or subtraction, we can check the number of digits after decimal point. In case of multiplication or division, we have to check total number of significant figures. Next, rounding of the numbers. So if the rightmost digit to be removed is more than 5, the preceding number is increased by 1. That means simply if 1.235 is there, the number which is to be removed is 5. It is 5 or more than 5. You can say 5 or more than 5. That will be equal to preceding number is 3. So it is increased by 1. Therefore 1.24. This is the rounding off. If rightmost digit which is to be removed more than 5 or equal to 5, the preceding number is increased by 1. Next, if the rightmost digit to be removed is less than 5, that means suppose if it is 1.234, then the preceding number is not changed. That means it will be equal to 1. The rightmost digit which is to be removed is 4, preceding number is 3. Therefore, answer 1.23. No need to change preceding number. So here 3 is changed to 4 because last digit is 5 or more than 5. Next here, no need to change 3 because the last most digit is less than 5. Next, if preceding number, that means if rightmost digit to be removed is 5, then preceding number is not changed if it is even number. That means, example, suppose 1.525 is given, 5 to 5. The rightmost digit to be removed is 5 here, 5. And the preceding number is even number, therefore no need to change. No need to change means here 1.52 we can write. Next, if rightmost digit to be removed is 5, wait one more, 1 point, suppose 535, and preceding number is increased by 1 if it is odd number. See here, which is to be removed is 5 and the preceding number is 3 which is odd, therefore increase 1. That means 1.5. So then second option becomes 1.234. Check here. 1.234, last digit is 4, preceding number 3. Therefore, no change. 1.23 only. Next, first one, 1.235. Last digit to be removed is 5 and preceding number is 3. 3 means odd. Therefore, increase 1. Therefore, 1.24. So, all points are covered here. Next, mole concept. That means about mole. So, 1 mole is collection of Avogadro's number of chemical species, that is 6.022 into 10 power 23 chemical species. So here chemical species can be or chemical units can be molecules or atoms or subatomic particles. So here subatomic particles means we will be having 3 types of particles: electrons, protons and neutrons. All these are chemical species or chemical units. Next, Avogadro's number is denoted with Na. 6.022 into 10 power 23 chemical units. Next, calculation of number of moles, small n. Number of moles equal to given weight in grams by gram molecular weight. Or in case of atoms, gram atomic weight. In case of molecules, gram molecular weight. Or number of particles given by Avogadro's number. Avogadro's number we can write 6.022 according to NCERT. Avogadro's number 6.022 into 10 power 23. Next, one more formula to calculate number of moles. Given volume in liters at STP by 22.4. So, gram molar volume 22.4. So, this is about mole and formula to calculate number of moles. Given weight by gram molecular weight in case of molecules. Given weight by gram atomic weight in case of atoms. Next, number of given particles by Avogadro's number of particles. Given volume in liters at STP by 22.4. Next, average atomic mass. So here average atomic mass equal to sigma relative abundance of isotope into its atomic mass divided by total abundance of isotopes. So this is very very important. Suppose I am taking a Cl as example, 1735, 1737. These are isotopes of chlorine. So from this abundance, so Cl35 is 75% available and this is 25% available. 75% 35, next 25% 37. So this is abundance. So therefore average atomic weight equal to, according to formula, relative abundance, 75 into 35, next 25 into 37 by total abundance, always 100. So we'll get this value as 35.5. This is the average atomic weight of Cl. Next, similarly, you can calculate average molecular mass. Molecular mass. So x1 m1 plus x2 m2 plus x3 m3. So where m1 m2 m3 are molecular masses of compound. Next, mole fractions x1 x2 x3. So you can add mole fraction x. Mole fraction x equal to number of moles of one component divided by total number of moles. Moles of all the components. This is mole fraction denoted with x or chi, Greek symbol. Next, empirical formula and molecular formula. So empirical formula denoted with EF, empirical formula, simplest formula. So empirical formula is the simplest whole number ratio of atoms of different elements present in one molecule. So for the empirical formula of glucose. Glucose molecular formula is C6H12O6. So therefore empirical formula becomes simplest ratio of atoms. CH2O, simplest ratio of atoms, CH2. So empirical formula gives information about simplest ratio of atoms of different elements, while molecular formula gives information about actual number of atoms of different elements present in given molecular formula. Simplest ratio, empirical formula, actual number of atoms, molecular formula. So relation between empirical formula and molecular formula. Molecular formula equal to some n into empirical formula. So here n can be calculated by this formula, molecular weight by empirical formula weight. Molecular weight by empirical formula weight. Next, after getting n, by multiplying n with empirical formula, we will get total molecular formula. Next, mass percentage of an element in a compound, or simply percentage of an element in a compound. With repeating question in minds, percentage of an element in a compound, we can write n into atomic weight by molecular weight into 100. Here n is number of atoms. of that element. AW, atomic weight. MW is molecular weight. In this way, you can calculate. So both are same, but I have given simple formula. Percentage of an element equal to number of atoms of that element into atomic weight of that element by total molecular weight into 100. Next, limiting reagent. Simply, the reagent or reactant which is completely consumed in a chemical reaction is limiting reagent. Reactant which is present in lesser quantity, or you can say the reactant which is completely consumed in a chemical reaction. Limiting reagent. Finding of limiting reagent is very, very important. So based on limiting reagent, you can calculate the masses of products formed. I will add here. Limiting reagent completely consumed or completely reacted. One more, excess reagent. Excess means which is present in large quantity, or which is left after the reaction. These two are very, very important. Limiting reagent is the reactant which is completely consumed, completely reacted. Excess reagent which is present in large quantity, which is left after chemical reaction. Next, percentage by mass or weight percentage. Weight of solute by weight of solution into 100. Next, it is temperature independent. Why it is independent means because the absence of volume. Here only weight is present. Weight is independent of temperature. Next, weight by volume percentage. Weight of solute by volume of solution into 100. Next, volume percentage. Volume of solute by volume of solution into 100. So these two are very, very important for calculations. Weight percentage and weight by volume percentage. Next, molarity. So molarity will be equal to number of moles of solute by volume of solution in liters. That means I will write given weight of solute. This is complete formula. Given weight of solute in grams by gram molecular weight of solute into 1000 by volume of solution in ml. This is complete formula. Similarly, molarity. Given weight of solute in grams by gram molecular weight of solute into 1000 by weight of solvent in grams. This is complete formula. Molarity and molality. So here this is very important. Temperature dependent molarity due to the presence of volume. So with increase of temperature, volume of solution increases. So as the volume increases, molarity decreases. Therefore, temperature and molarity are inversely proportional. So molarity inversely proportional to temperature. That means molarity temperature dependent. Next, but molarity is independent. Independent of T. Remember these 2 points. Next, units also very important. Moles per liter or molar units. Here units moles per kg or molal. Remember units also. Next, one more point. Relation between molality and molarity. Molarity equal to 1000 into molarity by 1000 into density minus molarity into molecular weight of solute. So many previous questions are there on this topic. Relation between molality and molarity. Next, mole fraction denoted with chi or x, which is Greek symbol chi. So mole fraction is ratio of number of moles of one component to the total number of moles of all the components of solution. Simplest formula, number of moles of A by total number of moles. Next, sum of mole fractions of all the components of solution will be equal to 1. This is unity condition. Unity condition. Next, normality. So normality, I will let complete formula here. Normality equal to given weight of solute in grams by gram equivalent weight of solute into 1000 by volume of solution in ml. This is complete formula. In case of molarity, gram molecular weight. In case of normality, gram equivalent weight. Next, units equivalents per liter or normal. Equivalents per liter or normal. This is also temperature dependence. That means if temperature increases, volume of solution increases, thereby normality decreases. That means normality and temperature are inversely proportional. Next, parts per million, ppm. So parts of solute by parts of solution. Then simply weight of solute by weight of solution into 10 power 6. Remember here, million 10 power 6, billion 10 power 9, trillion 10 power 12. Remember these three. Million 10 power 6, billion 10 power 9, trillion 10 power 12. If it is 10 into 10 power 9, we can calculate ppb. If it is into 10 power 12, we can calculate ppt, ppm, ppb, ppt. In case of m, ppm, parts per million. In case of b, ppb. In case of t, ppt. Million, billion, trillion. Next. For typical concentration terms, that means concentration of H2O2. H2O2 concentration can be expressed in two ways. Concentration of H2O2 in terms of percentage strength, in terms of volume strength. In two ways it can be expressed. Percentage strength means say 10%. Weight by volume of H2O2. Similarly 20% weight by volume of H2O2 and so on. Next, volume strength means 10 V of H2O2, 20 V of H2O2 and so on. These two are different methods to express concentration of H2O2. Next, a relation between percentage strength and volume strength. 17 by 56 into volume strength. Next formula, volume of O2 liberated at STB equal to volume of H2O2 into volume strength of H2O2. Here of H2O2. Very important. Volume of O2 equal to volume of H2O2 into volume strength of H2O2. Next, volume strength of H2O2 equal to molarity into 11.2, normality into 5.6. Next, for H2O2, N factor is 2. That means 2H plus ions. So again, we know normality equal to molarity into N factor, or normality equal to molarity into, in case of N factor, you can write 2. Remember this relation. Molarity into 11.2 or normality into 5.6. Next, oxidation state or oxidation number. It is the charge present on atom. Oxidation number means simply charge present on atom in the formation of a chemical compound. So here rules to calculate oxidation state. Here oxidation state of an atom in elementary state is 0. Elemental form, that means free state. It is nothing but free state. Next, oxidation state of an atom in molecular form is also 0. Elementary state or molecular form, oxidation state equal to 0. So here these are molecular forms: O2, Cl2, O3, P4, S8. These are elemental forms. Oxidation state is 0. Next, oxidation state of oxygen. For oxygen, we'll be having different oxidation states. -2 in case of oxide, -1 in case of peroxide, -1/2 in case of superoxide, and again +1 and +2. For oxygen, we'll have these oxidation states. Oxide formula O2- or -2. Peroxide O2 2-, superoxide O2-. So very important. Each oxygen -2 oxide, each oxygen -1 peroxide, Each oxygen minus 1 by 2 superoxide. Similarly, for hydrogen, we'll be having two oxidation state, plus 1 and minus 1. So when it will be plus 1? When it combines with non-metals. Minus 1 when it combines with metals. Next, for fluorine, always minus 1. Fluorine minus 1 always in its compounds. Elementary state, oxidation state is 0 for any element. But in combined state, we will be having these different oxidation states. Next, so hydrogen is combining with metal CaH2, therefore minus 1. Ca2 plus and hydrogen minus 1. Hydrogen in these compounds, here it should be minus 1. Here minus should be there. Minus 1. Next, CH4, it is combining with non-metal, plus 1. Next, interstitial compounds. These are interstitial compounds, therefore oxidation state is 0. Interstitial compounds. We'll get this information in D block elements. Next, oxidation state of Au, gold. Auric acid, plus 3. So for silver, plus 1, plus 2 are common states. For Au, plus 1 and plus 3 are common oxidation states. Silver and gold. Next, oxidation state of Br. In Br3O8, plus 6 and plus 4. Check here. This bromine, for this bromine, plus 6. This bromine also plus 6. And the middle one plus 4. So terminal bromine plus 6. Internal bromine plus 4. Next, oxidation state of carbon in carbon suboxide C3O2. Carbon suboxide. So here minus 2 and here plus 2, minus 2, plus 2 and here 0. So middle carbon 0 and terminal carbons plus 2. Carbon suboxide. Next, oxidation state of Fe in Fe3O4. Fe3O4 means magnetite. No. Fe3O4 means it is combination of two oxides, FeO and Fe2O3. Here oxidation state plus 2 and here oxidation state plus 3. Mixed oxide. Very, very important topic. Oxidation state. Next. Types of redox reactions. Repeating question in MSET, mains and advanced. So, intramolecular redox. Intramolecular means within the same compound, one element undergoes oxidation, other element undergoes reduction. Check here Cl state is KClO3 gives KCl plus O2. Here Cl oxidation state plus 5. Here Cl oxidation state minus 1. Therefore plus 5 to minus 1 reduction. Cl is reduced. But here oxygen oxidation state minus 2 and here 0. Oxygen is oxidized. Cl is reduced and O is oxidized. That means within the same compound, one element is oxidized, other element is reduced. Therefore, intramolecular, within the same molecule redox. Redox reaction means reaction in which both oxidation and reduction taking place simultaneously. Next, displacement redox. Here also same. Zinc undergoes oxidation and copper undergoes, that means Cu2 plus undergoes reduction. So simply oxidation means increase of oxidation state. Reduction, decrease in oxidation state. Next, oxidant. The substance which is reduced. Reductant, the substance which is oxidized. Remember these four. Very important. Oxidation and reduction are process. Oxidant and reductant are substances. Next, disproportionation. So disproportionation means same oxidation state will be converted to two different oxidation states. So here same oxidation state means intermediate oxidation state. That means one oxidation state will be divided into two different oxidation states. See here P4 example is given. P4 gives PH3 plus H2PO2 minus. See here on left hand side P4 molecular form of phosphorus 0 and here P minus 3 and here P plus 1. So 0 to minus 3 decrease in oxidation state reduction. Next 0 to plus 1 increase in oxidation state oxidation. Therefore same element undergoes both oxidation and reduction simultaneously. Or here single oxidation state is converted into two different. That means 0 will be dividing into minus 3 and plus 1 in this way. So 0 oxidation state is converting into minus 3 and 0 is converting into plus 1. This is the basic skeleton of disproportionation. Next, gram equivalent weight. So equivalent weight of an element. Equivalent weight of an element will be calculated by atomic weight by valency. Here valency is n factor. Valency is n factor. All denominator values are n factors. Similarly, equivalent weight of acid. Molecular weight by basicity. So basicity means number of H plus ions. Basicity is number of H plus ions in one molecule of acid. Next, equivalent weight of base. Molecular weight by acidity. Acidity is number of OH minus ions. Next, here basicity also n factor, acidity also n factor. Next, equivalent weight of salt. Formula weight by, so for covalent molecules we can use molecular weight. For ionic compounds we can use formula weight. Salt is ionic, therefore we are using formula weight. Formula weight by total positive or negative charge. Here total positive or negative charge is n factor. All denominator values are n factors. Next, gram equivalent weight of oxidizing agent or reducing agent. Here also simply formula weight by change in oxidation state. We'll have complete formula here. Equivalent weight of oxidizing agent or reducing agent or oxidant or reductant. Formula weight or molecular weight by change in oxidation state. So in acidic medium, KMnO4 changes to Mn2 plus. Therefore, here oxidation state plus 7 and here plus 2. Change is 7 minus 2, 5. Therefore, molecular weight 158 by 5. Next here n factor is, we will add here n factor. In case of element, valency of element. Next, basicity of acid. Acidity of base. Next, total positive or negative charge of salt. Next, change in oxidation state of oxidizing agent or reducing agent. This is about n factor. N factor calculation is very, very important. So equivalent weight of KMnO4 in acidic medium is, in acidic medium, MnO4 minus changes to Mn2 plus. So Mn oxidation state plus 7, here plus 2. Therefore change is 7 minus 2, 5. Molecular weight is 158. Next. So here gram equivalent weight of permanganate in basic medium. Basic medium it changes to MnO4 minus 2, Mn6 plus. Here MnO4 minus means plus 7. Plus 7 to 6. 7 minus 6, 1. Therefore n factor 1. So KMnO4, remember like this. In acidic medium it changes to Mn2 plus. Neutral or weakly basic medium it changes to MnO2. Strongly basic medium, or we can write alkaline medium it changes to, remember like this. These three are very, 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 very important. Then I will write like this. Neutral or weakly basic. In acidic medium it changes to Mn2 plus. Therefore here n factor, Mn oxidation state plus 7 and plus 2. So 7 minus 2, 5. 5 is n factor in acidic medium. Neutral or weakly basic medium. it changes to MnO2. Here Mn state is +4. So therefore here N factor 7 minus 4, 3. Next here Mn state +6 in strongly basic or alkaline solution. 7 minus 6, 1. So remember these N factors. Very important. Next, in case of dichromate, here always 6. In case of dichromate, always 6. But KMnO4 N factor depends on medium. For dichromate or chromate ions, always 6 N factor. N factor equal to 6. Next, equivalent weight of reductant, we know. Gram molecular weight by number of electrons lost, or we can take it as change in oxidation state. Oxidizing agent or reducing agent, change in oxidation state is N factor. Next, titrations. So what is meant by titration? So determination of concentration of unknown solution by using standard solution. So standard solution means whose concentration is known. Right here, known concentration. Standard solution means the solution whose concentration is known. So by using known concentration, you can calculate concentration of unknown solution by equating milli-equivalents. Milli-equivalents. Here N1, V1 equal to N2, V2. So this is about milli-equivalents. Or law of equivalence. So milli-equivalents of unknown solution, milli-equivalents of standard solution. Milli-equivalents of, say this is unknown solution, and this becomes milli-equivalents of known solution. Law of equivalence. Next again, normality equal to molarity into N factor. Remember this. In place of normality, we can write molarity into N factor. Next, one more point. In place of milli-equivalents, we can write milli-equivalents equal to, we can write normality into volume in ml, or we can write one more formula, weight by equivalent weight into 1000. Remember this. W weight is equivalent weight. So based on problem, we can use normality into volume or weight by equivalent weight into 1000. Next, redox titrations. So here two substances will be there, reducing agent and oxidizing agent. So check here, KMnO4 is oxidizing agent always. KMnO4 and K2Cr2O7 are oxidants, oxidizing agents always. Here Mn oxidation state +7, Cr oxidation state +6. Highest oxidation states means always oxidizing agents. Next, in acidic medium, it changes to Mn2 plus, therefore N factor 5. Next, so permanganate titrations, KMnO4 can be used here. KMnO4 is used to estimate oxalic acid or ferrous sulfate or hydrogen peroxide. KMnO4 is oxidizing agent. Remaining compounds oxalic acid, ferrous sulfate, hydrogen peroxide are reducing agents. So in case of redox titrations, we can write milli equivalents of oxidizing agent equal to milli equivalents of reducing agent, standard condition. So for problems, this can be used. Next, in dichromate titrations, potassium dichromate is always oxidizing agent, but in only acidic medium, it is oxidizing agent. So it can be used to estimate different compounds. That means, see here, potassium dichromate in acidic medium changes to Cr2SO4 thrice. That means Cr3 plus. Therefore, N factor will be always 6. So, potassium permanganate and potassium dichromate are used as oxidizing agents in redox titrations. The side by compounds will be reducing agents. Next, iodometric. Iodometric titrations, any oxidizing agent can oxidize Ki solution to iodine. Iodometric. Iodine will be released. Next, the liberated iodine is estimated with hypo solution Na2S2O3. That means here we can write, in case of iodometric titrations, milli equivalents of Ki equal to milli equivalents of Na2S2O3 equal to milli equivalents of I2. So, milli equivalents means normality into volume or weight by equivalent weight into 1000 weight. So, in iodometric titrations, indicator is starch. At the end point, that means equivalent point, it changes to blue color. Blue color changes to colorless. So, iodine with liberation of, when it reacts with I2, the color will be blue. But when it reacts with hypo, that hypo removes I2. Therefore, it changes to colorless. In the presence of I2, starch will be in blue color. But in the presence of hypo, that hypo removes I2 from starch. Therefore, colorless. So, this is the end of stoichiometry. See next chapter, thermodynamics. We will discuss synopsis of thermodynamics. So, lesson structure or important subtopics: work done in different process, irreversible isothermal process, reversible adiabatic process, irreversible adiabatic process. Next, sign conventions of Q and W. Q is heat, W and work. Heat capacity, enthalpy, entropy, free energy, and spontaneity of chemical reaction. We will discuss these topics. So, first one, examples of state functions. What are state functions? The thermodynamic functions which depend on initial and final states. Here, internal energy denoted with U, enthalpy H, entropy S, temperature, volume, free energy, number of moles. All these are state functions. Remember here, internal energy, enthalpy, entropy gives free energy. Internal energy denoted with U or E. Enthalpy H, entropy S, this one G. So very important topics. Next, examples of path functions. Work and heat. These two will depend on only path, independent of initial and final states. Next, examples of extensive properties. Extensive properties means these properties which depend on amount of substance. So all these are extensive properties. Next, intensive properties. The properties which are independent of the amount of substance. So all these are intensive properties. Next, isothermal process. Delta T, change in temperature is 0. Isobaric, delta P is 0. Change in pressure is 0. Isochoric, delta V is 0. And adiabatic process, Q, amount of heat is 0. Next, for cyclic process, delta U, change in internal energy and change in enthalpy will be equal to 0. Next, mechanical work or PV work, irreversible. Here it should be IRR, work irreversible. Minus P delta V, P is external pressure. P delta V, external pressure, change in volume. So delta V is final volume minus initial. Next, reversible work, integral of P external dV. Next, here this is very important. In case of graphs, total work done equal to area under the PV curve, represents total work done. Next, so work done in different thermodynamic process. So first, isochoric process. Isochoric means constant volume, work will be 0. Isobaric process, constant pressure, that means P external into TV. Direct formula. Reversible isothermal process, work done equal to minus 2.303 N0T log V2 by V1, or from Boyle's law we can write from Boyle's law, at constant temperature, T is constant, P1 by P2 equal to V2 by V1. From this we can write log V2 by V1 equal to log P1 by P2. Next, irreversible isothermal process, free expansion. Free expansion means external pressure will be 0. Therefore, work will be 0. Delta U 0, delta H 0. Free expansion of gas. Next. So, in expansion against constant external pressure, work irreversible minus P delta V, or V final minus V initial, delta V. Next, reversible process, adiabatic process. Adiabatic means heat change will be equal to 0. Work reversible equal to du ncv delta T, or nr by gamma minus 1. Gamma is Cp by Cv, Poisson's ratio, into T2 minus T1. Here it should be T, T2. It should be capital T, T2 minus T1, or P2V2 minus P1V1 by gamma minus 1. Gamma is Poisson's ratio. Next, final temperature can be determined by using this formula, T2 by T1 equal to V2 by V1, 1 minus gamma. or T1 by T2 equal to P2 by P1 power 1 minus gamma. So we know V2 by V1 equal to P1 by P2. Next, irreversible adiabatic process. Work done equal to minus P delta V into minus P external into delta V. So P external into V2 minus V1. Next, expansion work done in different thermodynamic process. First, isobaric, isothermal. Next, adiabatic. This should be adiabatic. Adiabatic. So this is based on graph on the area under the curve. I will write here graph. So this is P and V. So first isobaric, isochoric, isothermal and adiabatic. Isobaric, this one isochoric, constant volume. This one isothermal. Next adiabatic. Check here, area under the curve. First isobaric, area under the curve is maximum. Next, check here, graph should be like this. Next, area under the curve, this is isothermal. We will place graph here. Next, adiabatic. Now check here, area under the curve is maximum for isobaric. Work done is maximum. Here work done equal to area under the curve or area under the graph. Next, area under the graph is maximum for isothermal. Next, adiabatic. Next, isochoric. Next, first law of thermodynamics, delta U equal to Q plus W, where Q is heat absorbed. Let here plus Q means heat absorbed by system, minus Q heat released. Next, plus W work done on the system, minus W work done by the system. Remember the sign conventions. See here it is given, work done on the system W positive, by the system W negative, heat absorbed by system Q positive, heat given out by system Q negative. Next, heat capacity. So heat capacity is amount of heat required to raise the temperature of some amount of substance by 1 degree. Heat capacity equal to heat capacity C, heat absorbed by change in temperature. T2 minus T1 delta T. Specific heat capacity by mass of substance. This is the formula. Next, molar heat capacity. That means amount of heat required to raise the temperature of 1 mole of substance by 1 degree centigrade or 1 degree Kelvin. So here 1 degree means 1 degree centigrade or 1 degree Kelvin. Both are same. Difference of temperature is same in both the scales. So heat capacity means amount of heat required to raise the temperature of any amount of substance by 1 degree. Next, specific heat capacity means amount of heat required to raise the temperature of 1 gram of substance by 1 degree. Molar heat capacity. Amount of heat required to raise the temperature of 1 mole of substance by 1 degree. Remember these three. If heat capacity for n moles is given C, then Cm will be equal to here Cm, molar heat capacity, C by N for 1 mole. So heat capacity, specific heat capacity, specific heat capacity and molar heat capacity. Remember these three. Next, your heat capacity is Q by delta T. Specific means Q by delta T by mass of substance. Next, Cm is C by N. Say C is heat capacity for N moles. Heat capacity for N moles divided by N gives for 1 mole. Next, heat capacity at constant volume. Heat capacity at constant volume Cv equal to delta U, or we can write like this: amount of heat absorbed at constant volume equal to delta U. Amount of heat absorbed at constant pressure equal to delta H. Remember like this. Heat at constant volume equal to delta U. Heat at constant pressure equal to delta H. So from this we can write Cv equal to Qv by delta T. So Qv means delta U. Delta U equal to NCV delta T. This is important for problems. Delta U equal to NCV delta T, where N is number of moles, Cv heat capacity at constant volume, delta T difference of temperature or rise in temperature. Delta H equal to NCP delta T. Next, Cp minus Cv equal to R now. Next, specific heat capacity at constant pressure. Specific heat capacity at constant volume means R by M. M is molecular weight. Next, ratio of Cp by Cv is gamma. Gamma is Poisson's ratio. Poisson's ratio. So, for monoatomic gases, the value Cv and Cp were 3 by 2, 5 by 2 R. That is 1.66. Next, for diatomic gases, 5 by 2, 7 by 2 R. 1.4 gamma. Triatomic or polyatomic, 3 or 4 R. 1.33. Remember these values. These are important for problems and calculations. 3 by 2, 5 by 2 monoatomic, 5 by 2, 7 by 2 diatomic, 3 or 4 are triatomic or polyatomic. Next, enthalpy. So, enthalpy H equal to U plus PV. U is internal energy plus PV work. Delta U change in internal energy, delta H is change in enthalpy. The relation between these two is delta H equal to delta U plus P delta P. Or we can say delta H equal to delta U plus P delta V, or delta H equal to delta U plus delta Ng RT. So where delta Ng equal to number of moles of gaseous products minus number of moles of gaseous reactants. Very, very important. Next, heat of reaction at constant volume is delta U. Already have given this formula. That is simply constant volume heat is delta U, and this is QP equal to delta H. Next, for exothermic reactions, we know delta H is negative. Next, for endothermic reactions, delta H is positive. Sign convention for delta H. Next, here relation it is given delta H equal to delta U plus delta Ng RT, where delta Ng is change in number of moles of gaseous products and gaseous reactants. Only we must take gases. So enthalpy change for a reaction or heat of reaction equal to delta H of reaction. Enthalpy is summation of enthalpies of formation of products minus enthalpies of formations of reactants. Very, very important. If bond energies are given, delta H equal to bond energies of reactants minus bond energies of products. Next, in case of combustion, delta H, change in enthalpy of combustion of reactants minus change in enthalpy of combustion of products. In case of bond energies and heat of combustion, we can write reactants minus products. Remaining cases, products minus reactants. Next, Kirchhoff's equation. Relation between heat capacity and temperature. That in terms of enthalpy, in terms of internal energy. Next, change in internal energy can be calculated by using bomb calorimeter. Delta U equal to heat capacity into change in temperature into molecular weight by or atomic weight by given weight. Bomb calorimeter. In that, heat of combustion can be calculated. Next. So these are the terms. Change in temperature, M mass of substance, M is molecular mass or atomic mass. Next, efficiency of heat engine. Eta will be equal, here eta should be there. Efficiency denoted with eta equal to work by heat absorbed, work done by heat absorbed. Or we can write efficiency equal to delta G by delta H. Useful work done by amount of heat absorbed. Useful work done by heat absorbed. Very, very important. Next, T2 by T1, T2 minus T1 by T2, or 1 minus T1 by T2, or Q2 minus Q1 by Q2 in terms of heat and in terms of temperature. Next, standard state of substance is 1 bar at 1 bar pressure and 25 degrees centigrade. Remember that standard condition. Next, carbon standard form is graphite. Therefore, delta H formation of graphite is 0. So for sulfur, rhombic sulfur is standard state. Enthalpy of formation is 0. Standard enthalpy of formation is 0. Next, for elements in their standard state, delta H formation will be 0. That is important. Next, enthalpy of combustion is always negative. Calorific value of fuel, that means heat by weight. Calorific value means amount of heat liberated when 1 gram of substance is completely burnt with oxygen. Next. So this is the reaction. H2 gas will be converted to H gas. Here delta H is known as enthalpy of atomization. Here molecules will be converted to atoms. Enthalpy of atomization. So here in this reaction, CH4 gives C plus 4H. Enthalpy of atomization. Total molecule is converted into atoms in their gaseous state. Next, sodium solid to sodium gas, sublimation or enthalpy of sublimation. Next, here delta should be there. Delta H of solution. This should be like this. So many previous questions are there on this topic. Delta H of solution equal to delta H lattice energy plus delta H of hydration energy. Next, one more important point. Delta H lattice energy is always positive and delta H hydration energy is always negative, exothermic. Delta H of solution can be calculated like this. Next, enthalpy of neutralization. Amount of heat liberated when 1 gram equivalent of acid reacts with 1 gram equivalent of base. Enthalpy of neutralization. For strong acid and strong base, value is minus 57.3 kilojoules, minus 13.7 kilocalories. Standard. Next, heat liberated in neutralization reactions can be calculated by using this formula. Number of equivalents of acid or base into standard value 57.3. Next, enthalpy of dissociation of weak acid or weak base. So neutralization heat of neutralization of weak acid or weak base. Neutralization minus 57.3. Suppose I will give one problem. Suppose delta H neutralization of weak acid weak base is given as suppose 56 kilojoules. Therefore, delta H of dissociation equal to minus 56 plus 57.3 kilojoules. So 57.3 minus 56, that means 1.3. So plus 1.3 kilojoules of energy used for dissociation of that weak acid or weak base. In this way you can calculate. Next, entropy. So entropy is a measure of disorder or randomness of system. Disorder or randomness. Entropy of gas is always highest. entropy of gas. So entropy of liquid. Entropy of solid. In case of gas, randomness will be maximum. In case of solid, randomness will be minimum. In case of liquids, medium. Next, entropy change. Delta S is Q reversible by T. For chemical reaction, delta S equal to summation of entropies of products and minus entropy summation of entropies of reactants. For equilibrium, delta S is 0. Next, for spontaneous process, delta S total. Delta S total equal to delta S system plus delta S surroundings greater than 0. That means total entropy of universe increases during spontaneous process. Next, entropy of fusion. Delta S fusion equal to delta H fusion by freezing point or freezing temperature. Delta H of fusion by freezing point. Next, entropy of vaporization. Delta S vaporization, delta H vaporization by boiling point VP. Next, entropy of sublimation. Delta H sublimation by sublimation temperature. Next, entropy change of ideal gas. Delta S equal 2.3003 NCP. We will write here complete formula. Delta S equal to 2.303 NCP N into Cp log T2 by T1 plus 2.303 NR log P1 by P2 or 2.303 NCV log T2 by T1 plus 2.303 NR log V2 by V1. Entropy of ideal gas. Change in entropy of ideal gas. Here it should be V. So where Cp and Cv are heat capacities. Next. So at constant temperature, isothermal process, delta S equal to this. For isochoric process, isochoric means constant volume. Here it should be formula isothermal process. So 2.303 NR. Okay, next. Isochoric process Cv log T2 by T1. Isobaric process delta S equal 2.303 NCP log T2 by T1. Next, Gibbs energy. Gibbs energy denoted with G. So G equal to H minus Ts. Or change in free energy equal delta G equal to delta H minus T delta S. For reactions, summation of free energies of products minus summation of free energies of reactants. So delta G equal to minus T delta S total. You know, if delta S total increases, that means positive, delta G becomes negative. This is for spontaneous process. If delta G is negative, process will be spontaneous, and positive non-spontaneous, 0 at equilibrium. Next, relation between the most important for problems. Delta G naught equal to minus 2.303 or T log K equilibrium. This is relation between standard change in free energy and equilibrium constant. And one more point, delta G equal to minus NF E cell potential. Delta G naught equal to minus F E naught cell standard cell potential. So for spontaneous process, E cell or E naught cell must be positive. Delta G must be negative. Next, effect of temperature on spontaneity of chemical reaction. For spontaneous all temperatures, delta H negative, delta S positive. Spontaneous at non-spontaneous at all temperatures means reverse. Delta H positive, delta S negative. Next, for spontaneous at low temperatures, delta H negative, delta S negative. Next, non-spontaneous at low temperatures, delta S positive, delta H positive, delta S positive. Simply I will write here delta G equal to delta H minus T delta S. So if delta H is negative, delta S is positive, then delta G becomes negative, that is spontaneous at all temperatures. Next, if delta H positive, delta S negative, delta S equal negative, delta G becomes positive, that is non-spontaneous at all temperatures. Next, next condition, if delta H is negative, delta S is negative, both are negative. So delta G becomes negative at, see here, delta H negative, delta S also negative. Therefore, delta G negative, that means spontaneous at low temperature. Next, if delta H is positive, delta S is positive, then delta G becomes negative and spontaneous. So delta H positive, delta S positive. Spontaneous at high temperature. Remember these four conditions. And four. So these are the points given above. So very important for matching and calculation. So check here spontaneity. So for spontaneous at all temperatures, delta H negative, delta S positive. For non-spontaneous at all temperatures, delta H positive, delta S negative, reverse. If both are negative, spontaneous at low temperature, that is already given at the bottom. Non-spontaneous at low temperatures means both should be positive. Next, spontaneous at high temperature. Delta H and delta S both are positive. Next, non-spontaneous at high temperatures. Both negative. Relation between delta G naught and cell potential should be E naught, standard cell potential. So for spontaneity, if delta G naught is negative or delta G is negative and the cell potential is positive, then the reaction will be spontaneous. Very, very important. Cell potential must be positive. So this is about Gibbs free energy and spontaneity and non-spontaneity of chemical reaction. So this is the end of the chapter. In next video, I will explain one more chapter. All the best and thank you.